least the chances that I'll remember to talk about it at the end.
Is it what it is? Can I see my grade afterward?
Yeah. All right. So let's talk about Maxwell's equations. How far over? Just in view. All right. So one question is, I'm going to start into this, and then I'm going to turn around and say, have I done this part already?
Sum of dot A, basically this is the electric flux through a closed surface is equal to the total enclosed charge over epsilon sub naught.
Surely there's a marker that's darker than this. That's through a closed loop. All right, so these are Maxwell's equations. Have I gone through the conceptual creation of an electromagnetic wave, where I talk about one thing changing, cause another thing to change, cause another thing to change, and so on. And it gets into a loop. I'm getting no looks of recognition. Well, I'm assuming I haven't done it because everything that I've done, I am assuming also that sticks in your mind forever. Like childhood traumas. All right, so the first two actually are Gauss's, called Gauss's law. This is Gauss's law of electricity. Gauss's law of magnetism. This is Ampere's law with Maxwell's correction. And this is the part that Maxwell contributed. And this is Faraday's law. I don't know why I'm writing his name out and not the others. Actually, Faraday Lentz's law. We started out with Coulomb's law. Coulomb's law is in here. That you can. The only difference between Coulomb's law and this is just math and definitions. There's no physics in between the two. All right, so especially concentrating on these last two right here. If I take a charge, Q, and I move it over to here. If I think about it, I've got an electric field that started out with an electric field pointing in that direction. When I move the charge over here, that electric field is now pointing in that direction. Any bits of recognition yet?
Wasn't it essentially that they all cancel out and it just points perpendicular?
No, not the path I'm going down.
Okay.
All right, because it's a single charge. What's happened is that the electric field has changed. If the electric field has changed, the electric flux has changed. If the electric flux changes, I create a magnetic field. So, change in the electric field causes a change in the electric flux, causes a change in the magnetic field. If I have a change in the magnetic field, I have a change in the magnetic flux. And if I have a change in the magnetic flux, I create an electric field. And that's what the last equation here is saying, is that if I have a change in my magnetic flux, I'm going to create an electric field. When we first presented Faraday-Lenz's law, we talked about it creating an EMF or a voltage, but if I have a voltage, I have an electric field. So all of this chain reaction here happens because I moved the charge from here to here. Now I move it back. Matter of fact, I'm going to take that charge, I'm going to oscillate it back and forth, so that my electric field is constantly changing. So I end up with a change in the electric field, which creates a change in the electric flux, which creates a change in the magnetic field, which creates a change in the magnetic flux, which creates a change in the electric field, which creates a change in the electric flux, and we start to see somewhat of a cycle. If Q is changing, moving back and forth, my electric field is constantly changing, and this is a perpetual cycle. So what's happening is that I'm creating an electric field, which creates a magnetic field, which creates an electric field, which creates a magnetic field, and it self-propagates. Once I get it going, boom, it's off to the races. And this is the creation of an electromagnetic wave. Maxwell, by adding this one little correction right here, has now established that there could be such a thing as an electromagnetic wave. Up till this point, the whole idea of an electric field and a magnetic field was sort of a guesswork, a convenience. At this point, we can now come up with potentially some tangible evidence that electromagnetic waves really exist. So Maxwell took the next step and figured out what the speed was. And we will now go through the derivation of the speed of an electromagnetic wave.
Can I ask a quick question?
Yes.
For that, what is the reason for the subscript M in that second flux, and why is it not a B for magnetic field?
Because I flip back and forth between M and B for the subscript.
Oh, so they are the same?
Yeah, they are.
Okay.
Yeah.
So you created an electromagnetic wave by moving a charge back and forth? Like
Yes.
That's, okay.
Yep. So you rub a balloon on your head, get it all charged, and you move back and forth like this, you're now sending out electromagnetic waves off into everything. It is very low frequency electromagnetic wave. It's not going to do any damage, but you're still sending them out. Actually, you're just existing and having some body heat. It's sending out electromagnetic waves. All right, so let's get rid of this part because we need some room. I am going to remind you, and this is a convenience that we've already done this part. If I have a cosine curve, that the slope of a cosine curve is negative sine curve. Slope, so cosine curve looks like this. Negative sine looks like this-ish. Slope of a negative sine curve is a negative cosine curve. And then slope of a negative cosine curve is a sine curve. And then it cycles back. Yeah, that's right, we did this with AC. If I have a cosine, let's say I've got y is equal to cosine of 2x. What does that 2 do?
That's like makes it higher, or is it
Makes what higher?
this, like,
My cosine curve
the very top and the very bottom?
of the cosine curve?
Right.
2 out front would do that.
And then so that does more frequency, so more of them in the same place?
Yes. So if you picture that when we were doing AC, we talked about the fact that if we imagine that we have a wheel with a peg that's sort of moving around at some angular speed, if the angular speed is 1 radian per second, it takes 2 pi seconds to get all the way around. If it's 2, if omega, that coefficient there is 2, that means it's going twice as fast. So as this number gets bigger, it means that I'm going faster, which means I get more cycles in the same amount of time or space or whatever you happen to be measuring. So if I do just a cosine curve, that's just a normal cosine curve. If I do cosine of 2x, or p or q, or whatever I happen to be working in, I get twice as many in. 3x, I get 3 of them in. Yes?
So in our lab with the AC circuits, that coefficient was like 370 something.
Yes.
So that's like how much faster it would be going than a regular cosine curve.
Yes. What does this do to the steepness?
Makes it steeper.
Yeah. Matter of fact, it makes it twice as steep. And so if I have cosine of 2x, the slope would be negative 2 sine of 2x. Whatever number there gets just multiplied out front. The slope of that would be negative 4 cosine of 2x, because we multiply by 2 again. Then we went again.
Is it negative 8? Or no, it's positive because sine is, never mind.
Yes. And if you kept going, then 16 and so forth.
So that's like creating an electromagnetic wave. It just keeps getting.
If we kept doing slope after slope after slope, then that coefficient, well, it would keep getting bigger and bigger if this is bigger than 1. It gets smaller and smaller if it's less than 1.
Okay. Yeah, makes sense.
All right, so now the question that stumped a lot of my students from all different levels. Just the letter Q, this is not charge, it's just the Q. Q is equal to the cosine of P. P is an angle. And yeah. So I plot it out. Cosine curve. This would be 2 pi. This is my P axis, my Q axis. What is the period of this wave?
2 pi?
Anyone want to agree or disagree?
Yeah, I agree.
Either 2 pi or just 1.
I agree.
If we count 2 pi as one, like, cycle, I guess.
I think 2 pi, you're probably better off with 2 pi on this one, however, potentially not.
I guess we'll find out.
Yeah. All right, but Wesley, you were good with it?
Mm-hmm.
Anyone want to disagree? Or anyone want to disagree but don't know why?
That's usually how that goes.
That is a nice offer.
What's the wavelength? That's
It's just the measurement between the two peaks, right?
Is it? So what would the wavelength be?
2 pi?
It's the same answer?
Yeah, it does seem odd.
But, yeah, that makes sense.
Now, I'm assuming that most of you have done something like this in math class where you're given the equation and you're asked what's the period and what's the wavelength. It looks like one of you has done this, maybe three.
I just don't remember it.
Yeah, me neither. That was like a good 4 years ago.
Yeah.
Is the wavelength 2 pi or is the period 2 pi? I didn't give you enough information really to know. But most people say 2 pi for the first one, they eventually get around to it. And it's the second one where they suddenly, there's that moment of, yeah, something's not quite right.
Are they related by 1 and over?
No.
Okay.
Which one is the correct answer depends upon what is P. If P is time, then the period is 2 pi. If P is a distance or position, then the wavelength is 2 pi. So when we dealt with harmonic motion in the first semester course, we were just dealing with something that's oscillating up and down. We easily could just figure at some time t, it's in some particular position. But now we have a wave that is moving. We have to worry about both of them. And so, we need to come up with some way of expressing an equation of something oscillating back and forth which takes time and position into account. And you're in luck. Such an equation exists. I'm just going to do it generically. Since we're talking about electric fields, the electric field is equal to some maximum of value times the cosine. I could do sine, but I'm just going to do cosine because why not? Cosine of kx minus omega t. So we have two things inside here. If you want to throw in a phase shift, then you can throw in a plus phi at the end, but not necessary for what we're doing.
You said that this is the equation relating time and position?
Yes.
Okay, thank you.
This k here is known as the wave number. And the wavelength is just 2 pi divided by whatever k is. The period, omega here, quick review. I know we haven't really done this kind of stuff in a week. What is omega?
That's our angular frequency.
It is indeed. And the period is 2 pi divided by omega. So if I want to figure out the speed of a wave, if I have this form right here, I know, well, what is speed? Classic, simple definition.
Displacement over time.
Speed, I'm going to nitpick it.
Oh, just that's distance over time.
There we go, thank you very much. So if I think about the creation of a single wave, then the distance it travels is just the wavelength. And the time it takes to do that is just the period. So the speed of a wave is just the wavelength divided by the period. In physics 151, when we dealt with harmonic motion, the next step is then to say that's just wavelength times frequency. But we're not going that route. Wavelength is 2 pi over k. And period is 2 pi over omega, but since I'm dividing by this, I flip the reciprocal. So this is 2 pi with omega there. And so I end up with omega divided by k. So the speed of the wave is just whatever the angular frequency is divided by the wave number. And I'm going to write that off to the side over here because that is going to come back. Now we would have the speed of an electromagnetic wave if I knew what k and omega are, but they could vary. Omega and k are not set numbers. As it turns out, the ratio is, but the numbers themselves are not. Questions up to here? Brooke?
What is E sub m?
Maximum, whatever the maximum value of the electric field is.
Thank you.
So now, you get to witness an absolutely brilliant rendition of a three-dimensional wave in 2 dimensions. The electric field. It's on the baseline right there. That's not 3 dimensions yet. Here's the 3rd dimension. Now, the electric field and the magnetic field are they create each other and destroy each other. It's self-propagating. The magnetic field is gonna be perpendicular to this, so the next thing I'm gonna draw is sort of out of the board. Not particularly easy to draw, so I'm assuming in your notes, you will nail it. This is the magnetic field. And those 2 fields are perpendicular to each other. So just sort of imagine the electric field, magnetic field coming out like that. And then at some point they're going, let's see, then they go like that, and then like that. And that.
So magnetic field in your drawing is coming out of the board.
Coming out, in, out, in, out, in.
Okay. I'm definitely gonna nail this in my notes. I don't know about you guys.
I'm sure Brooke would be happy to draw it all for each of you and then sign it.
Please do it for me.
I'll pull the like, now I'm not an art teacher. Like I'm gonna,
I think the 2 different markers helps a little bit.
I think I'll do that.
Yeah, mine looks pretty awesome.
Yeah, I've got mine all the same color, so I'm not trying to differentiate that's gonna be fun.
As long as you can tell what it is.
Is it important, like, with that perpendicular angle, that magnetic field is not, like, I'm thinking of like the leading versus following thing that we did for the last